So let's do one thing as usual. This time I have a menti.com. So let me put this on chat. Respond to this. One second. Respond to this. How are you feeling today? Are you able to respond? Look at the chat. Amazing. Awesome. Good. Calm. Good. Very stressed, huh? Who is that? Why here? Great. Happy children. Excited always. Good. Great. Wonderful. Wonderful. Okay. Anybody who gets stressed? Remember, there is pressure, but stress is yours. Pressure is external. Stress is internal. So it's your choice to be stressed out. Enthralled. Okay. All right. Okay, folks. Good to share with you. I'm going to stop this class. Good, but mental health, no, yeah. Mental health also. Again, it's left to us how we help us ourselves. Okay. If you need more help, let me know. I'll connect you appropriately. Okay. I'm just a I can't understand this. I'm just a what? I don't know what it is. All right. Good, folks. Okay. Are you ready for today's session? Yeah. Okay. Shall we start? Why not? Some of you just put on your video so that I can see some real people rather than tiles. Okay. Sai Siddharth. Mohammed. Only two. All the others are like Dharmi is putting his hand on his face. All right. Okay, folks. Who else? Nobody else wants to show the face? Okay. All right. Megha, Siddharth, Janisha. Okay, I have a question for you. As usual, I'll start with something that I'll ask you. Okay.
Sir, how are we feeling today, sir?
Oh, yeah, I have to tell, right? As usual, I'm all excited to see you guys. So I'm going to say excited. Okay. I have a very simple question for you. You know the answer. So on the keyboard for the chat box, are you ready? Okay. Can you see? Can you see this?
Yes, sir.
I'm going to take one of them out. So I need to find out the center of gravity of this. Tell me away. I need to find the center of gravity of this. Give me a way. Tell me one way by hang it by the thread, then draw a line. Fantastic. Yeah, who is that? Okay, try balancing it. Yeah, try balancing is one idea. Sujit will get a mark, 1 point. Hang it by the thread. Mohammed will get a point. Repeat from another direction, correct? Try to balance on the finger. So try to try to balance two of them. Mohammed says use hang it with a pin. Dharmi, you take care of which two get 1 point each. Okay. So you're
Yes,
right.
sir.
It's a simple thing. So I'm doing what Mohammed has asked me to do. So I've just put the key over here so that it's a weight. So I take this. Shows that this is like this. Okay, I hang it. Make sure that this is not oscillating. I need to pick up my pen. Yeah, I need to draw that line. Fantastic. And then what do I do, Mohammed? I need to unmute and talk. Unmute and talk. Mohammed.
Repeat the same thing from like after rotating the object.
Okay. After taking another point, I do the same thing. All right. I got the center of gravity CG. Ha. I got the center of gravity. You can see it. Two lines met here. All right. Now, how would this? What do I do for this? Center of gravity. Moment.
You can do the same thing, right?
Same thing, sir. Yes, same thing. But what's the difference between these two? Let's see. Okay. All right. So I don't know what to do. Draw like this on the body. Okay. Then I take one more point, right?
Hmm.
Okay, one more point. Fantastic. Okay. Oops. What's the difference now?
Center of gravity is outside the object.
Outside. So it's not necessary that the center of gravity has to be this thing. Now, what is the principle that is used? Quickly on your chat box. What's the simple principle that has been used here? When gravitational uniform, I just need a very simple engineering mechanics answer. Moment, meaning moment, just expand a little bit. Moment, who said that? Ashwath. Moment. Pivot, okay. Moment about, exactly. Moment about what?
CG is always vertically below which the body is hanging. Okay, so what about it? Moment is fine. Give me a pakka answer. One of you, fast. Taking sum of moments, okay. Vertically below, total moment about CG is 0, okay. Moment about center must be 0. Moment about center, no. Come on. You're getting there, but not yet. What is it that is making the moment 0? Yeah, why is the total moment 0 there? Why is the total moment 0 when you hang it? Equilibrium is fine. There's something happening to the gravitational pull. Perfectly balanced on both sides. Okay, so what is the lever arm uh, of the weight? What is the lever arm of the weight? Not distributed equally is fine. So you know that the force is acting at the center of gravity. Distance from the pin is not the lever arm. The lever arm is parallel to the line of action. So the line of action is exactly going along that CG, and therefore the lever arm is 0. Fantastic. Okay. Good, folks. Just to wake you up, that's all. Let's move on now. I'm going to share screen today. I need about 15 minutes of your attention, okay? 15 minutes. I just want to give you an overview of how you look at things, okay? Are you ready? Are you ready? Okay. Are you able to see this screen?
Yes, sir.
Okay, just a second. How do I now make it full screen? Come on, full screen. All right. Okay. Okay. If you have a paper and pen or pencil, draw a spring. Draw a spring. Draw a spring. Done? Done? Did you draw a spring? Did it look like this? Did it look like this?
Yes, sir.
Yes. Okay. Anybody who didn't have this kind of drawing? Yes. Okay. Horizontal. Okay. No problem. But how come this? Okay. This a spring? Is this a spring? It's not a spring. Okay. What is
Sir,
a
it's a
spring then?
spring.
Okay. What's the spring then? What? How do you define spring? One of you on the chat box. Come on. You can also voice it. Oh no, yeah. Oh no, this is not a spring, is it? Okay, a spring is highly elastic. It has to be helical. Yeah. Who told you? Spring has to be helical. But that's what we have started to understand, right? Oh, spring. Oh, it has to be like this, right? We are sort of fixed to the form. But what is the function of the spring? The function of the spring is to, what does a spring do? Stores mechanical energy and delivers. Correct? Yes or no? Very good, Kinshuk. Now, tell me if that is the case, this is also storing energy and therefore there is a spring. Yes or no? Say yes. No. Megha, you said no. Tell me why not? If the function of a spring is to store energy and deliver it, does not work in compression. Oh, okay. That's what you're saying. Not all springs actually work in both directions, by the way. It acts in only one direction. Even in springs, that's the case, by the way. Supposing I showed you one of those springs where it was completely like this, no? Completely compressed like this, right? Completely compressed like this. You can't compress it anymore. So it's only one direction, right? So direction does not matter. But supposing I say, okay, this is a tension spring, you will agree with me? Why should it be proportional? Yeah, for storing mechanical energy, why should it be proportional to displacement? Who said I should be having it proportional? I just need to make sure that there is mechanical energy stored, right? And it gives back. When I remove the force, it comes back. That's perfectly enough, correct? Right? Now, let me ask you another question. Is this a spring? Are you able to see this? Is this a spring? So I'm going to do the same exercise. There is a force that is applied. It is storing the energy. When the force is removed, it is coming back. Isn't it a spring? Of course, yes. Right? And therefore, let's now take this spring form out of our minds. And if we have to ask, name a spring that does not look like this. Go ahead on chat box. The first 5 will get 1 mark each. Rubber band, okay, 1. Wooden stick, elastic band is already told. Wood stick is fine. 2 over. Any other. It doesn't have to be looking at like book, headphone. Fantastic, yeah. You got it. It does not matter whatever it is. If I take this comb and I do like this, it comes back, it is so. If I take this and let's say I bent it a little bit, though I'm not able to see it properly, if I bend it a little bit and leave it, it comes back. So everything around us is a spring. Our glasses are a spring, our bangles are a spring, our shoes are a spring, hairpin is a spring, door stopper is a spring, right? The table is a spring. The uh, the cables that are running for the elevator are the spring. Even the weights are springs. Screwdriver is also a spring. This just think of screwdriver as something which becomes a little softer. What will you see? As you twist it, between that end and this end, you are able to twist it, which means you are able to store some energy. And if you leave it, it comes back. Right? Even a cutting player has to be a spring. A touch screen has to be a spring. It comes back. Right? Everywhere there is a springing back. Even your stapler is a springing back thing. And therefore, now suddenly you see springs everywhere, right? All it has to have is a deformation that can come back, right? And in nature, in reality, almost 99.99999% of the things come back. One of them is asking about clay. I'll show you. This is clay. What's your name? Karthik. This is clay, okay? I'm bending a little bit and leaving. Just watch it carefully. I'm pressing it a little bit and leaving. I'm bending it a little bit and leaving. Can you see it coming back? Slightly. It may not be too much, right? And when it bounced, you were able to clearly see that it was springing back. Okay, so everywhere, whatever we are seeing, there is some springiness attached to every real object. Yes, some of them don't spring as much as the other, but the degree of springing is varying, but springs are there everywhere. I want you to realize this. This is a very important point that I'm making. Springs are there everywhere. So this gives me an idea, oh, okay, if springs are everywhere there, if I understand about springs, I'll be able to understand how all these operate, how to design, etc., etc. Okay, that's the point I'm making now. Let me move on. We did something in the last class. We took a bar like this, applied loads at different points, and then we wanted to find out the internal forces. Okay, and internal force diagram is what I have shown here. This is called the axial force diagram, correct? This is the axial force diagram. We did this by cutting one here, one there, and then looking at what would be the equilibrating force. This FAB, FBC, and FCD happen to be constant throughout AB or BC or CD, and therefore we could draw this. The internal forces could be negative or positive. What is negative, positive? We have a sign convention over here. The sign convention that I've shown here is pulling or the tension is positive, which means compression is negative. As you can see, this bar AB is in compression, BC is in tension, and CD is in compression. Very simple, right? Okay. I've done the same thing over here. All right. Now, these are the internal forces. And if I take only this bar, I see that it is under compression, right? If I take only BC bar, it is under tension. 30 Newton, how did I get? because 30 Newton is the internal force that I can see over here. Similarly, here it is 20 Newton. This bar CD should have 70 Newton. Is it compression or tension? Negative, which means compression. Okay. So I have one bar that is under compression, one bar in tension, one bar in compression. So far, okay? All right. Okay. So in compression, in tension. Okay. Now, so forces in each bar, I am able to find out very easily, no problem. Let's move on. Okay. Okay. Now, what I'm going to do is instead of this 50, I'll make it 25, 25, 50, 50 here. It doesn't make a difference, correct? Yes or no? Yeah. 1 second. Let me just have the chat box ready so that, yeah, very small displacement. You're right, Karthik. Now, by making it 25, 25 and pulling parallelly, it does not really matter. Don't write on mine, please, though I've given you permission. All right. Now the thing is, in this, supposing I replace these bars by individual springs A, B, B, C, C, D, will it make a difference? After all, we understood that even if I take a bar, the bar in tension and compression can be thought of as spring, is it not? So this is a spring AB, this is a spring BC, this is a spring CD without any loss of understanding. Why, Karthik, you're saying no? Rishabh also is saying no. Why can't I replace? It's the same internal forces that I'll get, right? As long as I
No, sir.
make sure
I meant
yeah,
that you can
you
replace,
can
like,
replace. All right.
there's no difference.
There's no, okay, that's why he said no. All right.
Yes, sir.
Thank you, Karthik. I don't know who is talking. Rishabh. Yeah,
Yes,
thank you. Yeah. Now, so coming back, I'm going to now change it to this kind of a thing. All right. So I'm going to shift to, instead of looking at as bars, I'm going to now look at them as springs. Okay. No difference whatsoever, right? I can maintain whatever I have done earlier, but now I'm going to call this as forces and springs. Okay. So let me now think of all these as springs. Okay. And then do the next exercise. Listen to me carefully as far as the next exercise is concerned. How do I come out of this? Give me a second. I'll just come out of this. Okay. I'll come out of this. Let me share the screen again. Okay. Are you able to see this now? Okay. So what happened to this? It had 20 Newton as the compressive force, and that has compressed the spring. Yes. And if I look at the middle one, this is under tension, which means it must have elongated the spring. Yes. So elongation is what I've shown here. And if I look at this bar or this spring has undergoes compression as its internal force, 70 Newton. I don't have to bother about these external forces anymore. And it gets compressed, as you can see here. Yeah. Now, in this, is it possible for me? So let me call this as delta. Let me use some other. Shall I use a darker green? Okay, a darker green. All right. So let's say this is delta AB. Are you able to see? Let's say this is delta BC. Okay. I need to move this bar. Okay. And this is delta CD. Okay. Now, how do I find out this delta AB? Oh, sir, I have, I'm going to assume that this is a proportional spring or a linear spring. Okay. Okay. What is linear spring? A, B, B, C, and C, D, let's say, are linear spring. If it is linear spring, then it is possible for me to find out what would be delta AB if you supply me with the stiffness of this spring. Yes, similarly stiffness of this, similar stiffness of this. Okay, for now, just to make things simpler, I'm going to use the same value, 1 kilonewton per meter for KAB, 1 kilonewton for meter for KBC, and this is also 1 kilonewton per meter. If you have a difficulty reading it, please let me know. Okay. Oh, that's a beautiful question one has asked. Sir, there should be 700 Newton here reaction. The answer is no. You cut it off here and draw it. 25, I'm sorry, 20 minus 50 minus 100 will give you whatever you're supposed to get. Okay? Are you with me? Yes or no? This is a 50 Newton. This is a 100 Newton. This is a 20 Newton. Directions matter. If you add all of this, if I cut over here, I will get this to be 70 Newton. Okay. All right. Okay. So I have now assigned some spring stiffness so that I can now write this to be delta AB is equal to, help me out, 20 Newton. This is in compression. So I'm going to use a sign also, minus 20 divided by KAB, and that is equal to minus 0.02. Correct? 0.02 is 1020. Yeah, 0.02. Similarly, if I do it over here, this will come out to be 0.03. This is a plus because it's in tension. And this will be 0.07. It is compressed. Okay. So I'm able to now find out delta AB, delta BC, delta CD. I have indicated appropriately over here. So if I use, let's say, a sign convention over here, let's say this direction is positive, then this is a positive value. So I'm going to say displacement of A with respect to B is equal to 0.02. Whenever you have a difficulty, you should ask me, okay? Remember, displacement of A with respect to B using this sign convention. Let's say this is along the I direction, this is along the J direction. I can put this as I over here. Yeah. So let me do that and see what happens here. This I already have 0.02, right? So let me take this. Give me a second. Yeah. Let me take this as I. This is J. So this is 0.02 I, right? This is in the other direction. What is this? This is U of A with respect to B, right? And what I'm going to show you here is U of B with respect to C, right? And that is 0.03. In what direction? It's in the other direction. So it is minus I. And similarly, this is U of C with respect to D, and U of D I know is equal to 0. Okay, so far so good. What is this equal to? This is equal to 0.07 I in the direction that is shown. Okay, now I'm clear. I have the displacements, relative displacements of each one of them. Now I can use geometry automatically and get. Sir, can you explain how you calculated displacements? Oh, very simple. See, what is U with respect to B? I have to fix B and see how much the A has moved. That is nothing but how much of compression has occurred in the spring. Right, Chaitanya? Right? Because this is fixed and I'm trying to find out how much A has moved. This spring is going through compression, So it is compressed by 0.02. Okay. 0.02 units here is meter here. So I can put meter over here. Clear? Just say yes, Chaitanya, if you have understood. Chaitanya. Chaitanya, are you able to understand it now? The displacement of this point. Okay, go the previous slide. So look at this. This spring alone has compressed by delta AB. What does it mean? Relative to B, this should move like this, right? That's what I've shown over here. I've not moved B. I've just made sure that the B is the same and moved only A. We can't see what spring here. Are you able to see my, oh, okay. Are you able to see my mouse? Vaishnavi, are you able to see my mouse? Folks, answer fast because time. Only cursor, right. Now what I'm saying is this spring has gotten compressed, is it not? Right? And if you look at it carefully, I have not disturbed B, which means A should now move to this point. Is it not? And therefore, that's what I'm calling as the elongation. Cursor is stationary, I see. Oh God, I think how many of you can see it moving now? I'm moving the cursor. Or screen is stuck.
So we can't see like now it's moving.
Okay, let me do it again. It may be because of the bandwidth that I have. How about now? Are you able to see? 1 second. Are you able to see the cursor now?
Yes, sir.
Okay, fine. Thank you. So what I'm saying is by fixing B, I can see that A has moved to rightwards by delta AB. Similarly, by fixing C, B has moved by delta BC. Similarly, fixing D, C has moved by delta CD, right? So in the next slide, that's what I'm showing. How much each one of them moved, but how much movement has occurred with respect to what point. And therefore, I have said, this is U of A with respect to B. This is U of B with respect to C. This is U of C with respect to D. Okay. Now I'm good to go. How do I find out U of C with respect to C as an absolute quantity? That's very simple. I can start from U of D and find out what is this. This I have done in engineering mechanics, right? And therefore, I know this is equal to 0.07, right? So 0.07 meter I is the movement of C. So I can now boldly say this movement is 0.07. Are you with me? Similarly, I can do U of B, U of C is equal to U of B is equal to U of C, sorry, U of C plus U of B with respect to C. U of C is already 0.07 I. Now I have to add U of B with respect to C, which I already have here, minus 0.03 I in meters. And that will give me 0.04 I, which means that this movement that has occurred is 0.04. Similarly, I can do for A, which is U of A, sorry, U of B plus U of A with respect to B, and that is equal to, I already have UB available, which is 0.04. Now I need to add this 0.02. So this is equal to 0.06, which means this moment is 0.03 not 6 meters in the positive I direction. Are you with me? This is basically the geometry of deformation. So I'm going to call this as geometry of deformation. I'm going to call this as geometry of deformation. Let me use these here. So for center materials, this is God. So far, okay? Is this clear? I just used the fact that this point connecting these two springs is one and the same. This point C connecting BC and CD are one and the same. I use that fact over here in order to be able to arrive at how much movement has occurred for each of these points A, B, and C. And therefore, I call it as geometry of deformation or displacements if it is in engineering mechanics. Here, since deformation has occurred, I'm using deformation. So that is got for you in SOM. What is this then? This is the constitutive property of the spring, right? Of the material of the spring. Right? So I'm going to use CO and P and tell you that this is the cop which is watching over, oh, okay, which material? I should use that material appropriately. So what did we do? I'm just going to go back. We first found out forces in springs. Then we used the constitutive property of these springs, right? And then what we did is we used the geometry of deformation, and putting them all together, I was able to now find out how much movement has occurred for each of these points. Okay. So in other words, what I have done is, in order to get the internal forces, I have used equations of equilibrium, right? Remember the first slide. Then I used constitutive property of the springs. And finally, I used geometry of deformation in order to find out the displacements of those connected points. Okay. Any questions? Let me stop here, ask you for questions before going ahead. Any questions so far? Any questions? So if I take a spring, and I pull with the force, let's say F here, and it deforms by a certain extent, let's say that is 0.1 meters. I take another spring, and I pull with the same force, and this moves by 0.2 meters. Which one is stiffer? The first one is stiffer. The reason is it has moved little, right? Or in other words, the stiffness property is associated with force per unit elongation. Okay. So how much is the force that I have to apply? So if I have this spring, if I have to find out the stiffness of the spring, all I have to ask is, what is the force that I have to apply so that this elongates by a unit length, whatever be the unit. Okay. You know this, I'm just repeating some of these because this will help me seamlessly go to the next step when we have continuous elements. Okay. So let me proceed further since you don't have any questions. Let's see how we can look at this. But what I need from here is not displacement of A or B, but I want displacement at the point of force, at the point where the force is applied. Okay. So let's quickly do this. What is the first thing I have to do? I have to look at internal forces, for which I'll use equation of equilibrium. Okay. That's very simple for me here. The force F if I look at this spring or this spring, both the springs are subjected to the same force F. Can you catch it immediately? So this is AB. Similarly here, I can state that BC is also going through the same internal force F. That's very simple. Let me have your chat on so that if you have any questions, you can ask me on the chat box. Okay. All right. I've applied EOE now. What is my aim? I need to find out how much this point C has moved. That's my aim. What will I do next? I will use the COP, the constitutive property. What will that give me? Oh, okay, there is this elongation. But tell me, sir, what is the spring constant or the stiffness of this? So KAB. Okay. And this is KBC. Let us say it is just like that. So that I can now write the elongation of AB is equal to KAB. No. Help me out. One of you on the chat box. F divided by KAB. Right? I'm sorry. KAB. Similarly, here delta BC is equal to F by KBC. Folks, one more thing that you notice here is I have not done a few things over here. So let me do that over here now. So let's say this on the absolute coordinate system. This is the positive sense. This is I, this is J. Okay. Now I can state that in the God, which is the geometry of displacement, UA is equal to 0. U of B with respect to A is equal to delta AB. Which direction? Along the I direction, correct? Similarly, U of C with respect to B is equal to delta BC along the I direction. In this case, both of them are moving in the same direction. So therefore positive. So what would be the displacement of C? That's the question I'm asking. That's very simple. It is nothing but U of A plus U of B plus U of U of U of C with respect to B. Am I right? Yes or no? If you say yes, fine. If you say no, you have to tell me why. I made a mistake here. One of you fast. One of you. I made one mistake over here. Okay, let's do it methodically. U of B is equal to U of A plus U of B with respect to A, which means this is 0. This is U of B with respect to A. And U of C is equal to U of B plus U of C with respect to B, right? And if I put this over here, I will get this to be U of B with respect to A plus U of C with respect to B. So what mistake have I done here? I should have put it like this. Are you with me now? Okay. I know it is very simple. I'm just telling you how methodically I'm going ahead with this. So I now know what is UC. Okay. So now what I'm going to do is I'm going to take this as a black box. This is a single spring. Remember, I'm applying a force here. And let's say this displaces by delta AC. Okay. from A to C. Okay, this is delta AC. What is delta AC here? It is nothing but UC because UA is equal to 0. Or if I have to be very clear, this is UC with respect to A. Yeah, so far so good. Should I repeat anything, folks? Fast. Okay. Now, what is delta AC? Okay. So, what is delta AC now? Delta AC is this. Now, I can substitute and I will get this to be, shall I write it over here? It's okay. This is F by KAB plus F by KBC is equal to delta AC, or in other words, F times 1 by KAB plus 1 by KBC is equal to delta BC. Now, how do I find out the stiffness? That's very simple. If I apply a force F and it displaces, elongates by delta AC, then I'm looking at force per unit area, which means that I will take it to be F divided by delta AC, which I can get here to be KAB, KBC, I'm sorry, BC divided by KAB plus KBC. Simple, no? Okay, so let me erase this a little bit so that we have room. For example, if KAB is equal to KBC, let's say is equal to K, what do I get? F by delta AC now happens to be, this is K, K square, this is 2K, so I'll get this to be K by 2. Original springs have KKH when they are in series. In series, when they are in series, their stiffness reduces. In fact, in this particular case, it has become half. Okay, what is this? This is the stiffness of AC. Simple, no? So now I can find out if there are two springs that are given to be in series, I'll be able to find out what would be the net stiffness of the combined two springs together. Okay. Now, 10 minutes into your breakout room. How about this? I'll make it simple here. I'm going to make this as just K here, K here. I want you to go methodically. Let me start the breakout room. Before that, let me just go. Let's see if I can show this. Let me show this diagram to all of you so that you can use it. Let's see. My computer, quick access. Let's see. Working problem. Okay. Okay. So I put that as a PDF file if you want to see in the breakout room. Please, not more than, I have only 5 minutes, so not more than 5 minutes and then come back. Okay. All right. So breakout room. Breakout room. Where do I do breakout room? Breakout rooms. I'm ready. I'm giving you 5 minutes. Start. Use the working problem that has been given here. You can have it ready for you to do this. Okay. It shouldn't take more than a minute for you if you're already there. Please go fast to your breakout room. Sandeep, tell Vinay Kumar to move.
Vinay, have you not assigned any room? Okay.
Hello, sir. Did you said something, sir? Did you?
Ria, why are you waiting here? You're supposed to go to breakout room. Aditya, Sandeep, let me just go to each of those rooms, just check out how it is going. Okay.
Okay.
All will be equal. All will be equal, no?
Yeah.
Because if
So-
the pillar, yeah.
So UB equals to delta AB.
Mhm.
Okay. Similarly, UC is UB given A is delta AB.
What you are taking as U? What are you taking as U?
I'm taking it as a displacement.
Okay, then okay. Delta is also displacement, so we can use one term.
Yeah.
Mhm.
So what
F
will be our
equals to
next step?
the spring constant is same for both or not?
It will
we
be
have to take
same for
different-
both. Since from
Oh,
reference,
nice.
they both move similar distance. So it will be same for both. Oh, okay. You're saying about K1. Okay, they both are different. Okay,
Okay.
one has KA and other has KB, I guess.
Oh. So then both displacement will be different then, because F is the force. Same force for them, and the spring constants are different. So yeah, it
I
should be
guess we
same.
need to do this in this way. Both displaces equal amount.
Uh-huh.
Displacement equals to force by spring constant,
Uh-huh.
and force adds up. Since force adds up, yeah, I guess the total force exerted on A will be equally distributed to force on B and on C.
Um,
Isn't it?
um, yeah. The spring constant will be added up because it is in parallel.
Yeah.
That we studied.
Yeah. Okay. Yes.
Then displacement equal to F by KB plus KC.
Now, one thing that I have to do now is EOE, GOD, and COP. God, COP, and this. Now, what I have to do here is in EOE, equation of equilibrium, I only know that the force in this member, so I'm going to draw that separately. This is CA. Let's say this is FAC. Okay. I'm going to assume that it is in tension. This is AB. This is FAB. Equilibrium tells me FAB plus FAC is equal to F. Geometry of deformation tells me that delta AC is equal to delta AB. COP is the same. FAC by K is equal to delta AC. FAB by K equals delta AB. Now, delta AC, delta AB are unknowns. FAC, FAB are unknowns. 4 unknowns. I have 1, 2, 3, and 4. 4 equations I can solve. Okay, I'll give this as homework to you. Is this clear? And you will find that the net force versus displacement for the combined effort is for springs in parallel, you will get it to be the addition of the stiffness of the individual springs. Okay, let's do the problem and get it right before we meet tomorrow. Okay, one word for checkout. You can tell me whether you learned something today or not. Yes? No? Go ahead. On the chat box. Okay. So enjoy, folks. Till I see you tomorrow. Okay. Bye.